The afternoon program. We've voluntold Martin to give the last little bit of his talk. So he's going to do that after the break from 3:30 to 4. And the panel then will be pushed back to 4 to 5 instead of 3:30 to 4:30. So, but before that, I have the pleasure of introducing Robbie King. He's going to tell us about SOMA Square Spectral Amplification, SOSSA. Thank you, Robbie, for being here.
Thanks very much, everyone. Okay, so I'll be telling you about SOMA Square's spectral amplification. And we have a nice, catchy acronym for it, which is pronounced SOSSA. I think that was the final pronunciation we landed on. So this is joint work with these 4 authors here, all of whom work at Google. My affiliations are sort of a bit in transition right now. So, okay, so let's get started. So this is a talk about quantum chemistry. So I think, when you read this title, maybe some people will get excited that maybe it's to do with, like, I don't know, PCP theorems or something. That's not the case, so I apologize for that. But you're stuck here now, so. Okay. So this is sort of the slide which gives the executive summary of what we achieved. So on this chart on the left here, we are sort of this final 2025 point. People often say, quantum computing will be useful for quantum chemistry, and one sort of nice example that people identified was this FIMOCO molecule, and that sort of became the sort of benchmark for when we'll be able to do useful quantum chemistry calculations. But there was a problem, which was like if you go back 10 years, and you asked, even if you have a noiseless quantum computer, and you wanted to run a single run of phase estimation on this FIMOCO Hamiltonian, and you compiled it using the best techniques at the time, the answer you got was that it would take centuries of QPU time, right? So even if you had a perfect quantum computer, even doing this useful thing would be sort of crazy expensive. So that was the case 10 years ago. And I guess the point of this chart is to say that we've sort of solved that problem. So if you were an economist or something, you would look at this chart and say, look, this is a log y-axis and years, and you would draw like a straight line and say, okay, we're making sort of good progress. Hopefully then there's another sort of log scale, which is the number of gates you can run on the quantum computer, which is going up, and at some point they're going to meet, and that's the year where we're going to do useful things. That's what a sort of economist would say. But each of these papers sort of came up with a new sort of a trick to make the algorithm cheaper. So the punchline that we put on LinkedIn and stuff is that we can now do quantum chemistry in a matter of hours, which is nice. That's sort of a human scale time, when the previous work was sort of on the order of days.
Robbie?
Yep.
Just to check, so what do you assume is the time to run a single gate, the top of the gate?
Yeah, I'm not the right person to ask about that, but sort of a reasonable estimate.
You don't remember, or?
I don't quite remember. I mean, I guess you could work it out from the calibration here.
Right.
I guess 10 to the 8 in 1 hour. So.
Yeah, because there is just a difference between like this sort of semi-pessimistic thing of kilohertz and this whole clock cycle.
Yeah, so I guess we're assuming like the number Toffoli's is around 10 to the 8 or 10 to the 9. That's yeah. And then here you can see these are the factor improvements we achieve over the previous state of the art. So you can see between factors like 5 to 10 usually. So that's sort of we do care about these constant factors, right? Like 10 hours versus 1 hour is a big difference.
Slightly optimistic, but just tiny bit. Okay.
Okay. So yeah, this is sort of the results, but What I'll talk about today is actually the technique behind these improvements we were able to make. Okay, but also, I guess, the organizers asked me to also put in some thoughts about like an outlook for quantum chemistry and what I think is important and what's solved and what's not solved and what's left to do. And I'm going to have my final slide on this final point, so we'll come back to it. But this is sort of the summary of what I think, where I think we are. And also, I should say this is not really my opinion as much as it is the opinions of my collaborators who know a lot more about quantum chemistry, such as Ryan Babish and Nick Rubin and people like that. So, okay, so now as a result of our work, we can do a run-of phase estimation in a matter of hours. So I'd say that's sort of good. From centuries to hours, we've sort of made good progress on that problem. And then this initial state preparation, people talk about a lot, but actually there's a recent paper from last year which sort of shows that actually this might be not too bad. I think they sort of found this MPS that seemed to have good overlap with for example, the Fumoko ground state. So it looks like MPS and SATSs are able to be sort of guiding states in the language of the previous talk. So that doesn't look too bad either. But what's the remaining problem? And the remaining problem, I think, is a big one, and one which actually does need a theory breakthrough, which is how to do this embedding. And we saw this in the previous talk with the example, sorry, in the first talk today with Martin's example of you have this oxygen active site or something, and then it's embedded in some bigger system. And how do you do that on the quantum computer? So that's what we'll talk about, hopefully at the end, which I think is sort of the thing that scares me the most about the potential for using quantum computers for quantum chemistry.
So, quick question: is initial state preparation, is that specific to Fumoko, or is that?
I think they looked at. I'm not sure. They looked at Fumoko and maybe some other molecules as well. A very numerical paper, obviously. Like they're just extrapolating things, and yeah. Yeah. Mm-hmm.
Right. Can I ask, so your target is the ground state energy now, right?
Yes.
So when you compare with classical methods, what exactly are you comparing with? I mean, you're showing THC or something else. What quantum chemistry you're doing? I think that will affect the classical runtime, right?
I haven't said anything about the classical runtime. I'm saying.
I mean, I thought in the last slides you showed the comparison with.
Oh, this one?
It's not.
Oh no, this is our improvement over the previous
I see.
best quantum algorithm. Yeah. Any other questions? Okay. Okay, so then here's an overview of what SOSSA is doing. So, a lot of people thought that this sort of curve had stopped because we'd found the best factorization of these 4-index tensors involved in the quantum chemistry problem, and there was sort of no more water to squeeze from the stone. But the sort of extra improvement we managed to find is that you can sort of realize that the state you're interested in is the ground state, obviously, which is at one end of the spectrum. So you don't actually need your compilation to work equally well on all possible states. You actually just want it to work well on this state. So that's sort of the thing. That's the thing we're grabbing onto and exploiting, is the fact that you can just focus on this low energy sector of the Hamiltonian. So that's the sort of way we get an improvement. And the way to harness that is to first express the Hamiltonian using a sum of squares form. And then after you've done that, you apply this procedure called spectral amplification, which sort of helps you with this low energy sector and gives you an improvement. So that's the sort of the SOS part and then the SA in the acronym. And then in this talk, I'll go over some analysis that you can do on the SYK model, which is a sort of toy problem involving random fermionic interactions. And this sort of, we'll see that you can achieve an asymptotic speedup using this procedure. So it's like a square root system size factor improvement. And this is sort of what convinced us to actually, take this seriously and really, spend, I guess, well, it was mainly Nick and Guanghao who were spending like a lot of time, coding this thing and like cluster compute and stuff. But it was sort of this analysis which, at least for me, convinced me that this is a good approach. So that the order sort of switched. That happened before, but the paper came after. But okay, and then of course, yeah, we showed on the previous slide that this achieves the state of the art at the moment for compiling quantum chemistry. Okay, so that's the introduction. And here's the outline. So I'll go over some background of how we think about compiling phase estimation in sort of with modern techniques. And then I'll go over the spectral amplification procedure and then the SOSSA algorithm. And then we'll look at this SYK toy model. And finally, I'll come back to this embedding problem, which is sort of a bit unrelated to the talk, but is sort of my suggestion for the most important problem to tackle next. Yep.
Compared to what?
Compared to the naive way of compiling the SYK block encoding. Yeah.
This might be a naive question, but I'm trying to learn. Would you consider the embedding problem, does it apply to things that are far more complicated, say like the active site of an enzyme? That's where you eventually probably want to go, right? Like really understand
That's right,
biological molecules. Is that why the embedding problem is a super important problem?
Yeah, I guess we'll come back to this at the end. That's not really related to this SOSSA thing, but it's how to treat sort of strongly correlated fragments within a sort of bigger system that is more free fermion, and how to do that. Yeah. But I mean, that's how people use embedding methods in chemistry today, and presumably we'll need to do some version of that with the quantum computer, because you can't. The whole thing is too many qubits to fit inside your quantum computer.
Yeah, do you now have a hand-waving argument that there's no more water to squeeze on the stone?
Yeah, good question. It's hard to predict these things, right? Like it's hard to predict technological progress, but I guess you could say that like you could also just say it's no longer the bottleneck at some point. But of course, the better you can do it would be nice too. Yeah, who knows? I don't know. I can't. Yeah, I have no argument for that. Definitely. I mean, yeah. Okay. Okay. So let's just go over a little bit of background about modern quantum algorithms for phase estimation and Hamiltonian simulation. And the sort of concept I want to sort of just introduce briefly is this concept of a block encoding. So a lot of people think about sort of trotterization and stuff like that, but I think the winning approaches for quantum chemistry, when you have these sort of highly connected systems, is actually to do this more modern, advanced sort of compilation, which is the following. So suppose I have a Hamiltonian. A block encoding is a compilation of a unitary U, so like a circuit for a unitary U, such that some scaled down version of H goes into the top left block of this unitary. That's my sort of, well, that's the definition of a block encoding. For some lambda, and you of course maybe want lambda to be as small as possible, right? If I'm shrinking the Hamiltonian a lot to fit it inside the unitary, that's going to cost me at some point. And yeah. And then the sort of theorem you can say is that using this block encoding, you can perform phase estimation on this Hamiltonian to some precision epsilon with a number of calls to this block encoding. And the number of calls scales like lambda divided by epsilon. So lambda is the thing I'm scaling by, and epsilon is the desired precision. And this uses this quantum singular value transform formalism. Okay, so we can sort of have this sort of slogan in the back of our heads. The total cost is the cost of the block encoding times lambda divided by epsilon. And this lambda is the main game that we can play. Right? That's sort of a lot of the improvements previously were figuring out ways to compile this block encoding with smaller and smaller lambdas. Of course, you can try and make the block encoding more cheap as well. Okay. So just to convince you that these things actually exist, I'm just going to show you one sort of canonical way to compile a block encoding, which is called this linear combination of unitaries. And I'll go quite fast over this slide because it's not too important, but for this talk. But okay, so suppose now I have a Hamiltonian, this is very generic. It's just a sum of a bunch of Pauli strings, right? So probably everything we look at is of this form. And the lambda that you can achieve using this LCU approach is the L1 norm of the coefficients. And you can kind of like see why that has to be a thing, because, for example, if all of these sigmas were like commuting and frustration free, then that would be the actual width of the spectrum. So you have to shrink by that amount if you're agnostic to what these sigmas are. And then, so the way that you compile this is you have a sort of prepare circuit, which prepares this state on a sort of ancillary register, and then you have a select circuit, which looks at that and applies the corresponding term. And if I do this prepare inverse select prepare, that is exactly compiling this block encoding. So that's a bit fast, but it's okay if you missed it. Okay, so what is spectral amplification? How do we do this? How do we sort of exploit the low energy sector? Okay, so the sort of first example you can consider is, now imagine my Hamiltonian is a sum of projectors. Right? So it's now written as some coefficients times some projectors. This is just the most simple case. So H is now manifestly positive semi-definite. We know the whole spectrum is in the positive side of 0. And you can consider this, I'll call it H sub SA. So this is a spectral amplified operator. And it's a rectangular operator, which has these entries here. And the key feature is that, in some sense, it squares to H. Right? So HSA is sort of acting as a square root of the Hamiltonian that we're interested in. And okay, so we can block encode this HSA operator into a block encoding. With the same sort of lambda being this. In fact, I think maybe there should be a square root here, actually. Apologies for that. Okay, but the point is you can block encode this HSA as well using a similar trick to the LCU. Okay, but this square root is very helpful. Why is that? And the reason is because the square root function near 0 is very steep, right? So imagine if I, instead of using the block encoding for h, use the block encoding for the square root of h, the eigenvalues or singular values or whatever that I'm working with have been sort of magnified by this steep part of the square root function. It's almost like I've taken a magnifying glass and zoomed in on the low energy sector and sort of exploded it. So once you sort of work out all of the error analysis and all that stuff, like, okay, so to estimate an eigenvalue of h, I only need an eigenvalue of the square root of that to some other precision that's more lenient, right? And then once you go through all of that, the thing you find is that the number of calls to the block encoding of this square root that we need, again, I think there should be a square root lambda there, is this thing in red, which is the square root of lambda times delta divided by epsilon. And what is delta? Delta is defining the sector that we're interested in. Right? So if we're interested in the sector of energies below delta, then you get this complexity for the how many calls to the block encoding you need. And so the way I like to think about it, at least, is that this root lambda delta is sort of an effective lambda. It's like the new lambda, right? It's the thing that's going on top of epsilon in like the number of calls to the block encoding. And so if delta is much smaller than lambda, right, then this is a big improvement over lambda. Right? If the sector we're interested in is very low energy, delta is very small compared to the L1 norm of the Hamiltonian, then you get a big improvement from this magnifying glass. Let's go.
Can you scale the advantage by taking a different route?
Okay, the question was, I should remember to repeat the question. The question was, can you get a bigger advantage by using a 10th root or something? We don't know how to do that, so we don't know how to do, we only know how to do square roots.
Why?
Because the way that we do it is we find a square root of the Hamiltonian. And the way that we're going to do that for general Hamiltonians, you'll see, is to use a sum of squares ansatz. But I don't know how to find an ansatz for the Hamiltonian which is like something to the 10. Yeah.
Because here you say fast phase estimation, but do you actually mean e to the IHT get faster? Or, because someone might use e to the IHT in some other subroutines.
Yes, yeah, that's true.
This is
Time evolution also improves
sorry.
by the same amount. This
Okay.
is also the same. Yeah. 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 So you can apply this to phase estimation, time evolution, lots of things.
That's time evolution within this low energy.
Yes, time evolving states that live in this low energy sector. Okay. So this was all for Hamiltonian, which is a sum of projectors, right? But that's not the case that we have in, say, in chemistry or in pretty much anything that's interesting. So, okay, so what's the issue? The issue is that, okay, so let's go back to the setting now of a Hamiltonian, which is not a sum of projectors, but it's a sum of Pauli strings, the same as what we're used to. So that's not in this form, right? That's not in the form of H equals a sum of PSD terms. But you can always sort of, in a silly way, get it into that form, right? Because energy is always relative, right? You always are picking some arbitrary zero. So you can just put the zero in a place, which lets you write the Hamiltonian, the shifted Hamiltonian, in this form that we had on the previous slide. So how you would do that for this in the most silly way would be to shift the whole Hamiltonian up by this L1 norm, right? And then if I imagine adding these multiples of the identity to this other side, I'll get some sum of projectors where these pi's are something like, if I have a Pauli like ZZ term or something, then this pi will be like identity plus ZZ, right? And that is a projector. That's a PSD term. So I can always do that, and then I can hope, okay, maybe if I just shift it up by this L1 norm and then apply spectral amplification, maybe that will be good. But the issue is that doesn't really work. And the reason it doesn't work is because generically this Hamiltonian H is going to be very frustrated. So this would work on a frustration-free Hamiltonian, right? If you had a frustration-free Hamiltonian and you shifted up by this L1 norm, the new zero would be the minimum eigenvalue. So you'd have this sort of lots of states in your low energy subspace. But if I shift off a generic frustrated Hamiltonian by this L1 norm, suddenly my whole spectrum has been shifted way to high energies, right? So I have no states in my low energy subspace, so that doing this square root thing doesn't hit anything, right? So that's the issue. Okay, so how can we use this spectral amplification on something like chemistry? That's the problem. Okay, any questions at this point? Okay. So now we come to, of course, this spectral amplification is I think, quite well known to people who are very familiar with QSVT, and actually it sort of goes back to this paper by Rolando and Sergio back like decades ago. So I think that's an old idea. But what's the innovation of how to use this in a useful way is the thing that we now call SOSSA. So it's going to harness sum of squares in a very important way. So the question that we can sort of start off with for this slide is, how can you efficiently certify a lower bound on the ground energy, or a lower bound on the spectrum of a Hamiltonian? Now you know how to efficiently certify an upper bound. All you need to do is write down a state, right, that has some energy, and you know that the lowest eigenvalue is below the energy of the state that you wrote down. But how do you certify lower bound? Well, it turns out there is a way to do that, and it's precisely using this sum of squares ansatz, right? So if I have a Hamiltonian H, and I write down an equation that's like H plus beta equals a sum of a sum of squares, right? A sum over j of bj dagger bj. And I literally write down what these b sub j's are, right? I write them as low degree polynomials or local operators or something. You can efficiently check this equation, right? You can expand the right-hand side and check all the terms match up. And this is a proof that the minimum eigenvalue is at least minus beta. And that's sort of what we want, right? For this spectrum amplification, we want to shift up by an amount that's closer, that's tighter, a tighter lower bound than minus the L1 norm. That's a very bad lower bound, right? So we want a better lower bound so that we have more states that are nearby to 0, and then we get more amplification. So that's sort of what this sum of squares seems to be doing.
By using low-order polynomials?
Do we, what, sorry?
Do you lose any information by using low-order?
That's right. So, okay, so let's go to the extreme and say we allow any operators for these b's, right? Well, then, I mean, if suppose I knew the minimum eigenvalue magically, and I said, okay, consider h plus lambda min, that is, in principle, some PSD operator. So that has a square root. In fact, I don't even need this sum over j, right? I can always express that as the square of its square root, right? But the problem is that square root is going to be some crazy non-local thing that I have no way of writing down. So this is an ansatz for doing this, and this beta won't be quite, tight with the minimum energy. It will be sort of a bit loose, and that comes from the fact that these b's are restricted to be low-degree polynomials. Does that answer the question?
Yes.
Sorry, the question was, do we lose anything by forcing the b's to be low-degree polynomials? Okay. So then, we would like to find the best lower bound. So we would like to minimize this beta. Sorry, yeah.
So even if you knew what the right beta was, like just shifting by beta times identity wouldn't, like it's not clear that would give you the terms like as projectors, right?
Oh, okay, so
Each individual term would be a demonstration of each term. Maybe I'm confused.
are you confused between?
Question, right?
Sorry, the question was, if I just shift by beta, that doesn't guarantee me that I'm going to be a sum of projectors?
Yeah.
Well, okay, I mean, are you confused between the difference between the sum of squares and the sum of projectors?
Maybe, yeah.
Okay, so it turns out we can do spectral amplification if it's a sum of squares.
Okay.
So it's sort of a bit more general than a sum of projectors. But this is going to be fine for us, yeah.
Can you say what you mean by low degree polynomial and what?
Okay, so that depends, right? That's actually your choice. But you should choose something that's natural for the problem. So for example, if I was doing quantum chemistry, then I should probably take my B's to be like low degree in the fermionic creation and annihilation operators or something. Or if I'm doing some sort of something on qubits with Pauli's, I should take it to be some low degree polynomials in the Pauli's. So something that's going to be natural for the application.
Which is also sort of the same thing as you have on the left-hand side.
Exactly. Yeah. So the question was what are these B's low degree in? And yeah, the answer is whatever H is usually a low degree polynomial in some monomials, and we should just choose the same monomial. So, yeah.
But is it criteria that you can get block encoding for each BJ?
That's right. Yeah.
Okay. So low degree in the sense that each one can be different.
That's right. So the question was, what is the actual requirement? The actual requirement is that we can block encode efficiently these BJs. That's what's going to let us block encode the square root of H plus beta. And that's right. This low degree is just a way to guarantee that we can do the block encoding.
Do you know the number of terms J you need? Or how do you choose the number of terms?
So, right, that gets on to my next point. So I'll come back to that. The question was, how do we choose the number of BJs that we're going to have in this sum of squares? Okay, so we'd like to find the tightest lower bound beta. So we'd like to minimize this number beta, which looks like a kind of scary optimization problem. But in fact, it turns out this is literally a SDP. It's literally a semi-definite program to minimize this beta. So in fact, it's actually provably classically polynomial time, which is sort of ironic because it's pretty difficult in practice. So it's sort of one of those situations where there's a computer science proof that this optimization is classically efficient, but in fact, Guang Hao and Nick had to spend many hours of cluster time in order to actually do this optimization for chemistry molecules. But okay. And yeah, so an interpretation of what this is doing, this minimization, and oh yeah, I should come back to this question of like, what is this, how many BJs are we going to have? And that will just come from the solution of this SDP. So often they're sort of low rank. It's the rank of this gram matrix or whatever, yeah. Okay, so what has this done? This has allowed us to, yeah, so okay, so what is this doing? I think a nice way to understand what this is doing is it's finding a low it's finding a low frustration form for the Hamiltonian, right? I've written the Hamiltonian H plus a shift in a way such that hopefully the ground state is close to satisfying each of these terms. That's sort of an interpretation. Okay.
So this is not necessarily tight though. Like you said, like you won't necessarily find the best beta.
That's right. But the better beta is, the better the amplification will be. Okay, so this is the new strategy. This is the SOSSA algorithm. We're going to optimize this ansatz, shift by the smallest amount we can beta, and this beta will hopefully be much better than the naive shift. And therefore this delta, this low energy parameter, will be much smaller if this beta is indeed a good lower bound, a tight lower bound. And then hopefully this effective lambda will be improved. Okay, so I guess this slide will answer the question from before about, so we can equivalently define, we call it this H sub SOSSA, and it's this rectangular operator here, and it's also, by observation, we'll just square to H plus beta. Okay, so now we have a new cost, which is this cost of the block encoding for this H sub SOSSA times square root lambda times the gap divided by epsilon. And this is the new cost that we want to optimize in step 1.
Suppose a chemist told you what beta should be. Does that help you?
Good question. I think that might help with the optimization. Okay, so the standard optimization would just be to like find the best lower bound. But in fact, the way that Guang Hao and Nick got these really good compilations is that they actually optimize directly this total cost, which is more complicated, but they had tricks to do that. So because you really want to take everything into account. Yeah, so maybe that would help. Yeah. The question was, would it help if you knew the beta ahead of time? Okay. So that concludes the description of the algorithm. So next we'll just see an analysis on this SYK toy model. Yep.
So is there like a trade-off between how tight you want your beta to be and then how much your block encoding costs? Like, for example, you could do the absolute smallest, right?
Yes.
But then your block encoding.
Yes. That's a great question. So the question was, is there a trade-off between making my ansatz more complicated and getting a better beta, but then it costs more to block encode the beach sub j's? And that is very much a trade-off. So we're going to see actually an explicit example of that at the end of the next section. Yeah, that's a great point. So yeah. Yep.
This sum of square introduce extra errors. For example, like if I want to estimate Hamiltonian to the chemical precision, this basically means like your SDP need to achieve that precision, right?
No, so actually this representation is an exact representation. There's no plus epsilon in the ansatz for the Hamiltonian.
So this is like you obtain this sum of square by SDP?
Yeah. Oh, you're saying there's going to be some numerical precision in the SDP solution? That's true.
I mean, like the chemical precision is pretty small. So like the precision like incurred by your SDP should be even smaller than that, right? To make sure like even you can, to make sure like the energy is pretty.
That's true. But yeah, that's true. But that's sort of something you have to make sure of in your classical preprocessing. But the SDP is converged to within a good. The question was, is there any extra error incurred by using this ansatz? And yeah, you need to be careful of that. But it's a classical optimizer, so you can sort of GPUs are pretty good. Yeah.
So this is not really an SDP, right? Because the objective function seems not really.
That's right. The question was, this is not quite an SDP once you have this total cost as the objective function, because it's not linear, and that's true. That's true. Okay. Okay. So since it's a theory community, I thought I would just go through this analysis that convinced us that this is sort of a useful technique. And we looked at this SYK as a toy model. So what is the SYK model? It is literally of this form, where of the form that we were looking at previously, where these G's are Gaussian coefficients, and then we'll have every single degree 4 Majorana term present in this Hamiltonian. And I like to normalize by 1 over n squared, as that's just a convention about how I define energy units. And these Majoranas, you can sort of get them from the fermionic creation annihilation operators by taking a plus a dagger and a minus a dagger, and they're sort of they're like Pauli's basically. Think of them as Pauli strings, and they all mutually anti-commute with each other. That's how they're defined. And this is sort of a model for like a very strongly connected, interacting fermionic system. Okay, so some facts about this SYK model, just to sort of calibrate how we're thinking about it, is that with this normalization, the spectral norm is actually going to be order root n. So that's just that's just a fact. But you can sort of just by looking at it see that if you did this LCU, this sort of if you tried to shrink it by its L1 norm to get it inside a unitary, the L1 norm is going to scale like n squared. That's because all of these coefficients are order 1, and there's n to the 4 of them over n squared is n squared. So it's much bigger, right? The whole spectrum is within a window of root n, but the L1 norm is like going like n squared. Okay, so what is the key fact? The key fact is if we use this degree 2 sum of squares, so if we use this ansatz where these b's are degree 2 polynomials in the Majoranas, in fact, this achieves a lower bound that scales not like n squared, but like n. So it's a factor of n better than the L1 norm. Yeah, and the proof of this is very short. It just needs like one fact from random matrix theory to prove this. Okay, so that means that our delta that's going to go into this amplification. Sorry, yeah, Robin.
Is the spectral norm upper bound easy to see, or is that just like a non-trivial fact?
I think that's actually quite non-trivial to prove, but I think that physicists have believed it for a long time. I think it's one of those facts. The question was, how do you know that the spectral norm is root n?
I guess matrix concentration to give you.
Yeah, I guess the matrix turnoff bound maybe is.
Are you saying there isn't a mathematical proof that this spectral norm?
There is, for sure.
Oh, there is?
Yeah.
Okay.
In fact, I think maybe the matrix turnoff.
Up to constant. I mean, up to constant, you can get it pretty.
Yeah,
close,
like a constant times root n, you probably can just use matrix turnoff inequality. I think. Yeah. Okay. Okay, so this delta that's going to go into this amplification, this effective lambda, is actually now order n instead of what would be n squared if we use the whole L1 norm. And in fact, a funny fact about this situation is that the spectrum is all within a factor of n. It's actually like all temperatures this holds because the spectrum is only width root n. But that's a pretty quirky feature of just like using this model. So I wouldn't read too much into that for like what it says about chemistry. But yeah. Okay, so just ignore this bottom bit for now. Let's just look at the top bit. So if we did this LCU approach, we would have the lambda would be n squared. But once we've done this degree 2 sum of squares compilation, our root lambda times delta is n to the 3 halves, which is a whole factor of root n better. So it's an asymptotic improvement. So when we found this, that was sort of the green light to go ahead and like put a bunch of resources in to try it out on chemistry. Okay, so this is a brief aside, which I do have time for, I think, which I guess is answering an earlier question, which is about this trade-off. So you can ask the question like, okay, still this SOS is not even getting the right scaling, right? Like the actual minimum eigenvalue is scaling like root n, but actually this degree 2 SOS doesn't even know that. It can only certify a lower bound that's scaling like n. And this is actually a question that Matt Hastings asked in his paper with Ryan O'Donnell. And what he showed is that if you go one level higher in this SOS hierarchy and you go to degree 3 polynomials, suddenly degree 3 does know the correct scaling. Degree 3 can certify this root n lower bound. So for some reason that I think no one understands yet, the degree 3 seems to do much better on SYK than the degree 2 SOS. What's the problem? The problem is if we use this degree 3 SOS, suddenly the lambda is much worse because we have many more terms and we need to sort of encode all of them. And in fact, sort of in a weird coincidence, if you use the degree 3 SOS, you actually end up getting the exact same scaling as if you had just done LCU in the first place. So the worse lambda sort of cancels out the better beta, and you get no improvement. So that's sort of a cautionary tale that just getting the best beta possible is not the best thing to do, as the previous question observed. I think it could be a very exciting direction to try to find a way to actually use this better, Matt Hastings' better degree 3 SOS to do even better on chemistry. Yep.
So the scaling that you built, I mean, I guess that's sort of naive scaling that comes from, like, if you just assume you have some arbitrary degree 3 polynomials, yes? But did you ever like try to numerically implement it? Maybe there is some miracle so that it's much more compact?
I suspect, yeah, that's a good question. Is there some trick you can do to improve this lambda as n cubed? Because that is the most naive thing. Maybe. Maybe not for SYK because you still have all of these Gaussians, so it's pretty random. Maybe for chemistry there is, right? So and that would be the next point on this to answer Umesh's question about what more water is there to squeeze. I think this is possibly some new hope.
So your takeaway lesson from this is that doing quadratic SOSSA is also the right thing for chemistry?
That's what we did, yes. So we then did quadratic SOS. Also because it's just the cheapest thing that will work. But yeah.
Can you mix both?
Mix both of these, degree 3 and
have
degree.
a few cubic terms.
That's actually what. So I should repeat. The previous question was, did you use this analysis to inform the fact that we're using degree 2 on the real chemistry molecules? The answer is what I said earlier. Okay. The new question was, can you mix and match the degree 3 and degree 2? In fact, that is what Hastings does in this paper. So he actually uses the whole degree 2 algebra, and then he picks out a linear number of degree 3 polynomials and just puts those in. So he calls it a fragment. So he doesn't take all n cubed of them. He actually only takes linear many and puts them in. But still, I don't know how to block encode these things with a cheaper than n cubed cost. Oh, yeah, sorry.
In this aside, what is the value of delta? Like, why is delta not squared?
Delta is going to be square root n.
Yeah, but then you wouldn't get n squared, right? You get
it would get square root of n cubed times.
Root n?
Oh,
So what's
That is a good point.
Like it would still be worse, I suppose, than the degree 2 case.
That's a good point. Let me think. Maybe I got the lambda wrong. I mean, I definitely remember it coming out as being exactly the same, so I think I must have got the lambda wrong. I think the lambda must be like n to the
3.5.
5 halves or something. Yeah. Oh, wait. 7 halves.
7 halves, yeah. Okay.
I think I actually remember that. I think lambda might be, yeah. So I'll work it out afterwards and get back to you. Sorry, that's a good observation. The observation is that this actually doesn't compile, so apologies for that. Okay. Okay. So that's the end of the SYK analysis. Okay. So I think I'm going to finish early, actually. So the last slide is just to come back to this point that I raised at the beginning on, what I think is the remaining problem to solve in quantum chemistry that is the most scary along the sort of roadmap to useful quantum chemistry algorithms. Okay, and I should say that I'm a little bit waving a not an expert flag here. This is mostly just sort of my best parroting of Ryan and Nick, but so here goes. Okay, so in the real world, we don't have these nice sort of isolated molecules that we just want to know the ground state of this isolated molecule. In fact, we usually have these bigger sort of things, and we want to know there's some sort of catalyst or something, and there's like a strongly correlated active site. And that's the one where we need the quantum computer, because that's where all of the DFT and everything fails. But the whole system is very big, way too big to fit on any quantum computer you could imagine. So then the idea would be to use the quantum computer as a very high precision solver for the active site, and in the same way that people today use coupled cluster, as we saw in Martin's talk. So that has a big problem, though. And the problem is actually quite easy to understand once you sort of wake up to it, which is the following. So when you do this embedding method, you have this fragment, and the environment imposes an effective Hamiltonian through the boundary of this fragment. And but you actually sort of need to do this sort of recursive self-consistency thing. So you actually need to sort of solve the environment, impose a Hamiltonian, solve the active site, and then read out this wave function and update the effective Hamiltonian, because there's sort of a back reaction. And you need to do this over and over recursively until it converges and everything is self-consistent. That's how these embedding methods work. And in order to do this, you need to read out a bunch of information from this wave function of the active site, from the solution of your high precision solver. So if I run a coupled cluster or something on the active site, I literally have a representation of the wave function in my classical memory in like an Excel spreadsheet or something, and I just sort of read out all of these amplitudes that I need, and then I can, if that takes a few hours, I can just start the next run straight away, right? The next coupled cluster of the recursion. But the quantum computer is not the same, because if you run the quantum computer for a few hours, right? We just saw at the beginning, like a single run of phase estimation is going to take hours, right? So I run that, but then I don't have a wave function in classical memory. Instead, what I have is a coherent wave function in my quantum memory, and I can't just read it, right? I have to then measure it. So a naive way would be to then you have to do some sort of RDM tomography or something on this wave function that you have, but that needs many measurements, right? So if I want to read out, say, the 4 RDM, there's n to the 8 terms in the 4 RDM, and that's going to be a multiplicative factor, right? That's like the shot complexity. So that's a few hours times n to the 8, which is pretty terrifying. So we don't want to do that. And so I guess the opportunity for theorists in quantum chemistry, in my opinion, is there a way around this? Is there a native way of doing these embedding methods on a quantum computer coherently, which avoids...
Check the self-consistency through the quantum computer? Is this what you mean? Or?
Yes, that's right. That's right. Okay, yeah, so that's the end of my talk. Thanks so much.
In your fate estimation, do you assume that the initial state is confined to some low energy subspace in your numerics in the beginning?
The numerics at the beginning, you mean the executive summary, this one?
Yeah.
This is just a single run of phase estimation. It doesn't involve the fact that you have to repeat if your initial state is not good.
But doesn't your algorithm get better the lower energy your initial state is, essentially?
Oh. You're asking what delta did we take for this? We took the one that's just to the ground energy. Yeah.
Just to follow up on that, does this, for example, you want to run phase estimation with this SOSSA method, does it mean that your, let's say, kind of guidance state, your initial state, has to also be within this delta window, or like you would somehow, if you know that the ground state is within delta window, that's within delta?
Yeah, so that's a similar question. So the question was, if you're running phase estimation on the guiding state, do you need the whole guiding state to be supported in the low energy sector, or is it enough that you amplify the ground energy?
Yeah.
I think it's enough to amplify just the ground energy, actually. And the reason is because we're really just filtering that part of the guiding state anyway, and then we're just trying to get that estimate within some epsilon, and that epsilon is blown up by this amplification. So, yeah.
So the scary part at the very end, that applies to like all quantum chemistry approaches. It's not just a phase estimation approach. Is that right? Like this embedding problem. That seems to be.
Is the question? Okay, so the question was, does this embedding problem apply to all quantum chemistry? You mean all quantum chemistry methods, or all quantum chemistry calculations of interest?
Let's say the latter.
Quantum.
Yeah, like if we want to do some sort of quantum computation to do this, you have to do this embedding. That's a huge problem, it sounds like, and that has nothing to do with the fact that we're doing the phase estimation approach with a guiding state. That sounds like this is a more general problem. Is that right?
Oh, I think I actually had a conversation earlier today with someone who I forgot their name, but they were telling me that if you don't do phase estimation, if you do some other approach, I think it's this idea of like sampling and then diagonalizing the Hamiltonian within some sampled subspace or something. I think maybe that gets around this problem if you don't. But the sort of mainstream like phase estimation to prepare the ground state, I think this is a problem for those mainline sort of methods.
So will this not work much worse if like you just put the entire system, including the thing where it's embedded into?
I think it's way too big. I think it's like thousands of orbitals.
It will be much worse than this.
Well, but also, I mean, for the foreseeable future, we're going to be limited by number of logical qubits.
Sure.
Just imagine a hemoglobin molecule.
Just ask a question.
So I think the mainstream embedding method actually only uses one argument, which is n squared terms, and some of them can be measured in parallel. If you only need like a finger representation.
Right. Yeah. So I think that's true. So that one. Okay. So the question was, I think maybe the mainstream embedding methods only use the one RDM, which seems okay because that's only n squared terms, which you can probably squeeze down to n if you group things correctly. And I think the point is that if you have a strongly correlated fragment, like if the fragment is strongly correlated with the environment, you do need these higher interactions. And those are sort of the classically hard cases. I think that's what someone who knows more would say to that question, I think. But
what are the like properties we should expect one of these polynomials to have to be efficiently blocking coded?
I see. So the question was, what is the minimum requirement on these polynomials so that we can efficiently block encode them? And I mean, if it's a low degree polynomial in things that you can block encode, then you can block encode it. Yeah, so like if you can block encode the individual pieces and you build a low degree polynomial out of them, then you can block encode the low degree polynomial. So pretty, anything you can imagine basically, I think. Oh.
Is that it?
Oh, I think that was one more.
I was just ask if your like active site is strongly interacting with whatever's outside. Like, isn't this something we would probably want to avoid? As in, I'm assuming whatever you pick as your active site should be like within itself strongly interacting, because like this is like the what quantum computers are like supposedly good for. So I assume you want to like create your cut to be like very sparse, but like very strongly interacting.
I know what you mean. I don't think I'm not sure if I have anything to add to that. I think
What was the question?
The question was, I mean, was about this last slide again, which is like, you know, haven't you chosen the wrong fragment if you're going to need these higher order terms? But yeah.
All right, let's thank Robbie again. All right, we'll pick up again here promptly at 3:30. And just a reminder, there's a little change in schedule. Martin has graciously agreed to come back and give us